Good afternoon, everyone. Thank you so much for joining us. My name is Desmond Martin. I am the Chief Learning Officer at NextWaveSTEM, and it is my very good pleasure to have you for another one of our free webinar series, Bouncing Back with Learning Games, the importance of hands-on learning both inside and outside of the classroom. This is an awesome opportunity we have here at NextWaveSTEM to really talk about what the future might hold for us in the wake of the past 16 months, but also this chance for us to have an amazing opportunity to think about this emerging technologies in some ways that we might not have thought about before. I'm really, really excited for the webinar today. Before we do jump right in, the first thing I want to cover are just a couple of house rules. First and foremost, that we are in webinar mode. That means that you won't be able to I won't be able to hear your face or see your voice. No problem for you, though, with respect to communicating with me. You can jump into the chat. I'm going to drop just a message so that everyone has that chat notification that pops up in your Zoom. If you have any questions or comments or commentary throughout the course of the webinar today, please feel free to drop that right into the chat, and we'll make sure that we get your questions answered live on air. The second thing is really particularly for our Illinois educators. In the state of Illinois, today's webinar session counts as one PD credit hour with the Illinois State Board of Education. Following the webinar today, you will be receiving an email that has a few things in there. The first is a copy of the slide deck that I'm using for today's presentation. The second is an actual link to the recording. This webinar and all other webinars that we've done at NextWaveSTEM are going to be uploaded to our NextWaveSTEM YouTube channel, and we'll give you a link directly to that recording. But the third thing you'll receive is your certificate of participation. You want to fill that certificate of participation out, complete the survey that's included in the email as well, and you'll be able to claim those PD credit hours. With all of that being said, we'll go ahead and we will jump right in. A great place to begin is right at the beginning, just a little bit more about who we are in NextWaveSTEM. We are a 3-year-old STEM education startup company that believes that your children may save the world. I am not exaggerating when I say that. And the reason why I'm saying that, and I say that with such conviction, is that we are facing some critical challenges throughout not just the United States, but throughout the entire world. We are, at least in the United States of America, coming to a point where hopefully we're winding down in the current pandemic, but also living in stark realities about what the next pandemic might look like and what we'll do to avoid that pandemic. We are also dealing with the existential crisis of food insecurity paired along with climate change, and those two ideas are interrelated. There are climate refugees living in the United States who have had to migrate from where they live in the United States right now. Big, big questions, things that you are reading in your local and national news publications. However, I believe, and we at NextWaveSTEM believe and agree with Bill Nye, the science guy, when we think about how important science, technology, engineering, and mathematics are to solving some of those most difficult problems. At NextWaveSTEM, we believe that it's possible to get to those solutions because our students have the opportunity to participate in STEM from an early age. We want to see them change their STEM identity. Students going from just being consumers of technology to being the producers of technology and technological solutions. And we also understand that in order for that to happen, you, the educators, the administrators, those who are making the biggest difference and their direct impact on our students have to have the tools and access to technology yourself in order to be able to see those goals come to fruition. At NextWaveSTEM, it's part of our job to help make that happen. I briefly introduced myself just at the top of our webinar. I'll give a little bit more of a formal introduction. Once again, my name is Desmond Martin. I'm the Chief Learning Officer. I've been with NextWaveSTEM now for over 3 years, almost since the very beginning, and I help facilitate the professional development and curriculum development here at NextWaveSTEM. But I want to focus specifically on what we can do for you, what we can offer in the context of bouncing back from our learning gains, especially in the context of career and technical education, something that we don't talk about very, very often here at NextWaveSTEM, but something that we're talking about more and more because of how important and how directly connected emerging technologies are to career and technical education. We want to take a look at a specific example. And our specific example will deal with computer-aided manufacturing through the lens of 3D printing. And we're going to take a look at what we can do remotely here with respect to career and technical education. Many of our students are just itching for the chance to get back to their devices, learning more about emerging technologies. And then finally, we want to talk about remote and hybrid learning models for those gain opportunities. What kind of changes can we make? What things can we focus on really to help supercharge our students' learning even before they get back with us in the upcoming fall? Now at NextWaveSTEM, we have three particular technology pathways and tracks that we develop our curricular material towards. Robotics and artificial intelligence, drones, and 3D technologies. We are K through 12 solution, but today we really want to focus on the CTE pathway. I'll have a chance to talk a little bit more about what we do later on in the webinar and how what we're doing in the CTE space and how you may be preparing your students for futures in the CTE space can really be enhanced by what we offer at NextWaveSTEM. All of the work that we do, our course material, 21st century skills focused with alignments and NGSS, as well as Common Core Math and ELA. We want to make sure we give you a solution that's really going to work for your particular needs. So let's start thinking about and considering learning loss in the current context. It is July 6th, 2021, and we want to consider where our students have been and what it means for us to gain. In order for us to gain, we have to start by considering, at least in some kind of framework, what we may have lost thus far. When we consider learning loss, on average, students have lost somewhere around 5 months of learning time between March 20 and June 2021. When we're considering that loss, what we are considering are average numbers of, to be straightforward about it, days that students were not in school, and those days that could not be remediated through emergency funding or legislative maneuvering or even decisions by the school board, things that we're not empowered for as we were making the transition to hybrid and remote learning. Many school districts throughout the country, it took us some time. It took us some time to understand how we were going to be able to conduct classes with our students. It took us time in order to develop ourselves as educators, just even to realize, hey, what is it going to take for me to actually deliver classes to students via the internet? And beyond that, we have to consider our own student needs and their struggles as well. Many of our students throughout the United States struggle with having consistent devices at home. Many students struggle with having consistent internet at home. Many of our students struggle with the social and emotional skills that were necessary to get into class. And we see this really being magnified and emphasized in a couple of different areas, especially when we think about the context for career and technical education, which is so often focused on having access, practical access to technology. When you consider what's happening at the high school level, students were seeing their opportunities to practice these skills and learn about these two new technologies and some older technologies completely removed. If you can't go into the building, you don't have this opportunity now to work on a robot. You don't have this opportunity to learn about health sciences. You don't have this opportunity to learn about agricultural sciences. You don't have the opportunity to learn about manufacturing or becoming a machinist. Those specialized and increasingly specialized skills are removed from you just from lack of access to the facility. The same thing with the case with respect to community colleges, where CTE is really being offered from a dual degree perspective. When facilities are closed, the access to equipment is not there, and career and technical education becomes much, much more difficult. And we're going to sound like a broken record. The same thing is happening. And when we think about what's going on with career sensors, those third-party areas where students can go and learn and get certifications, attend networking events, and be recruited, things that couldn't happen in person, that there's time that took to have remediations in terms of learning those opportunities. It took some time, and that time adds up for our students. Now, when we think about the actual loss in time, adding up to those 5 months, we understand that it's not flat across the board. There are disparate impacts depending on student populations. When we think about African American and Latinx communities, those numbers go from about 5 months, even up to 6 and 7 months. And we see those numbers decrease when we think about Caucasian students and students of Asian descent. They get lower, 4 months. A lot of that comes into respect to things like cultural responsiveness for the material that we're delivering in the first place. If there's not a direct connection even to motivate our students to continue on with their education in the face of something that's really, really difficult, in the face of something that's completely shaped and rocked the way that they think about their education, specifically in the course of the pandemic, it's difficult now to really remediate that. Social and emotional learning becomes really difficult as well. We see not only at the middle school level, but also on the high school level, students who are dealing with the real trauma, trying to check in, and it can be difficult for our students, it can be difficult for us as educators to stay checked in. And once again, just like we're removed from resources with respect to technology and access to technologies at schools, that lack of resources really shows up with respect to our home learning and support as well. Not only do I not have the technology if I'm in the place of a student, I might not even have the adequate room, the physical space that's quiet in order to continue studies here. So when we think about not only CT from this general perspective, but we're thinking about the specific populations and communities that we're serving, it's really important to consider now, okay, how do we step up our efforts that much further for our communities that may have been more deeply and more aggressively impacted? With that being said, we consider the next normal. And this next normal applies not only for what we're doing in the CTE space, but what we should expect to see and what we will more likely than not see going forward with respect to K through 12 education generally. Device distribution became a huge, such a massively important part of our response to this pandemic. Chromebook distribution was done in 77% of all school districts here in the United States of America. If you didn't have a computer, if you didn't have a way to access the wealth of the world's information, Chromebooks, internet hotspots became such critical ways to let that happen. And so much of what we did with respect to our own teaching pedagogy had to be adjusted as well. We were teaching through Zoom. We were connecting our students through Zoom and breakout room and through chat and through email and through all these digital tools that can honestly become really monotonous. But what we saw that was not monotonous was in the lack of actual hands-on technology usage. Simulation became so critical and so important to what we're doing in the technical education space. That's where we think of the idea of technology kits. This was happening in a much smaller scope, but we saw some school districts who are sending out robots, sending out drones, sending out microbricks and Arduinos and Raspberry Pis, and actually allowing students to work from home with some tools that they had available to them. We're very, very fortunate that now, as we are coming once again to a slowdown in this pandemic, more of our students are able to follow CDC guidelines and get back hands-on with their technology. But in the absence of that, in a potential future where that may be difficult once again, we're seeing more and more of a capacity for student at-home hands-on learning being built. So it's something really, really cool to see. So now what we want to do is think about what this means from the perspective of making things really, really flexible and really, really available for our students in a career and technical education space. And the whole idea here deals with design and simulation. More and more of the work that our students that they'll be doing in the future will not only be in hands-on development of tools, machines, and skills, but also now the ability to simulate and design solutions ahead of time. This becomes a critical part of the work that they'll be doing in the future when they're solving some real-world problems. And the particular example that we want to take a look at is in this space of 3D printing. Working with this emerging technology, some technology in the 3D printing space is barely older than we are. This is the same time, around the same time Apple computers were founded back in the 80s. This technology was just coming into a place, just being invented. We can use this example of 3D printing to really focus on what our students might experience in this hybrid scenario, where they need to be flexible and get some of this learning back. Supercharging our learning in the future will not only be just going back to the way things were, but even taking the best of our practices in the height of the pandemic when we're designing and simulating, and also applying that to our student work. So we have this question where we should consider how students might practice skills in computer-aided manufacturing. Well, before we answer that question, we have to understand how computer-aided manufacturing from the specific technology of 3D printing works. When our students are doing 3D printing, they're not just doing one thing. They're not focused on one particular skill set or pathway. They are not relegated to a particular way of doing things, but they are dealing with a technology that has lots of broad implications. What they'll be doing is combining computer-aided design principles, CAD specifically, really, really robust skills with some very, very useful career-connected certifications, along with engineering. And when we think about engineering in this context, we're almost always thinking about product design and actual physical product engineering as opposed to processes. Both become extremely important, but if our students are making hard and fast physical things, especially something for production, for mass production, these skills in computer-aided design become really, really important. When our students work with 3D printing, they now have some other opportunities because of the ways in which computing has advanced even in the last decade. Students are able to engage cloud-based design. That's something we're going to take a look at in just a moment here. They can connect not just with software that they have to pay for and download and make sure that their computer is fast enough to run, but now, as long as students have a stable internet connection, they can have access to some extremely powerful tools for 3D design. Students are taking cloud-based design and marrying that to the engineering design process, actually thinking through what a customer needs, brainstorming and ideating, doing research, actually building or designing, and then building that design and testing and iterating. All those things come into play. And we're also adding a particular wrinkle now in the context of the printing space because we know more about what it means to print remotely and engage with remote printing services. Not having a 3D printer no longer becomes a barrier to actually doing 3D printing. That's something that we'll talk about a little bit more as well. So as our students are building these skills and engaging these certifications, they're going to find applications in architecture and construction, but also in the energy sector, manufacturing, and agriculture and food and natural resources. Yes, we're even going to use 3D printing and computer-aided design to make more food that people are going to be able to eat. We are finding ourselves in the space where the technology is offering an abundance of opportunities for our students. So in order for them to start, they have to develop their skills remotely. And there are three particular skills. When students do 3D printing, they shouldn't think about 3D printing as just a set process. What they should consider is that 3D printing is a three-step process. Three broad strokes that may be very different based on the technology and application, but they are almost always exactly the same from the really broad spectrum of what they will actually do. The first is the actual design. Regardless of what the object is or its application, all 3D printing starts in computer-aided design. The ability to take what we imagine in our mind, what might be laid out for us in constraints, whether that's designing a new valve cover for a car, experimenting in the automotive space, if it's designing a new irrigation valve in the agriculture sector, or if it's designing a flexible implant in the medical sector. All these things start off as something that lives in our mind, just ideas that we have about solutions based on the research that we've done. And our students have to translate those designs, maybe first into something two-dimensional, something that's sketched out on a piece of paper more traditionally, but then built into 3 dimensions, something that lives in pure math that we can then translate into something that our printer can do something with, can actually work with and produce. The second step, and I just alluded to that, is the actual slicing. You can imagine in this world of 3D printing, in this particular skill set, that 3D printers are kind of, once again, like cars. You'll find many different models with many different capabilities, different sizes, different speeds, even working with some different materials, but they all basically do the same thing. And that's translate this raw 3-dimensional file into now a 3-dimensional object. Because every machine is slightly different, the translation, that code that takes that raw math and turns it into instructions from the machine will also be slightly different. And as our students come to understand more about material sciences, as they come to understand more about the physics of 3D printing, and as they marry that understanding with their design skills, what they're able to simulate, what they're even able to design, they're now going to be able to really design even this slicing process, because there are an infinite number of ways that we can really define instructions for the machine, being able to change the way that we design for our applications and that we slice for our applications can really make a huge difference in the final outcomes for those printed parts. And then once they've really got that translation, they're ready to print, they have to physically transform the printed material into an object. And the amazing things about this is that we're growing day by day with kind of materials that we can do 3D printing with. Once upon a time, it was just plastic, just PLA, very soft, very brittle, extremely versatile material, extremely cost-effective material. But there's only so much that you can do with plastic. Our students are now printing with the metal, actually printing 3D printed metal parts to replace broken machinery out in the field. They are printing in water bottle plastic and hard ABS plastic, in nylon, and with wood filament, and even with biomaterials. These different materials are the future of technology. We want to empower students to be able to understand how to design for these applications, slice, basically programming and 3D printing for these applications, and then print to solve problems for these applications as well. So a great example that we can consider is a variable spring rate. And for this example, we're actually going to jump away from our slide deck and jump into a cloud-based 3D design software. Many of you may even be familiar with this particular piece of software. It's called Tinkercad. Now, the reason we want to jump into the software is actually considering from a CTE perspective, the kind of flexibility that this software gives us and the basic design skills that allow our students to really grow in their skill sets. Tinkercad is designed with 3D design and 3D printing from the outset. So a really important thing to understand with respect to 3D design is that our students need to understand constraints with respect to size and volume. What we have is a space in 3 dimensions that allows me to rotate around. And if you're familiar with other NextWaveSTEM programs, you might recognize this setup in particular. In this setup, we see a very, very common microcomputer called an Arduino. This is a very slightly different board that we use in our products and in our courses. But the Arduino microcomputer is a perfect example of a programmable, low impact, low cost solution for students who are learning about circuitry and learning about coding. That computer will be connected to 2 motors. In this case, our 2 motors would be driving wheels on our NextWaveSTEM robot. So what we're seeing here is a 3D mock-up, an exploded, blown out view for what we would find on the inside of a robot that we actually use in NextWaveSTEM courses. Why is this something that we want to show? We want to show this because what we're seeing are actual parts, pieces, components, and physical considerations that students would need to take when designing new solutions. If that's working in the manufacturing space or in the robotic space, computer-aided design starts there. We're able to take common 3D objects that live in the technical space, Arduinos, and in this case, our micromotors, and actually space them out. I can pull these out and I can see specifically how big the space is that I'm taking up. In this case, it's 123.41 millimeters. And if I want to adjust the amount of space that this particular assembly is taking up, I can easily jump inside of Tinkercad and just using a few mouse clicks, bring these motors much closer together, much like we would see on our actual MBOT. This may be the difference between dollars per unit. It may be the difference between hundreds of dollars for a small production run or thousands of dollars for a small production run. In the long term, it could save a corporation and a company tens of thousands of dollars in materials, in packing materials, in shipping costs, in tariffs and fees, just because of the way we've made slight changes to our objects in 3D design before we ever putting things together or pieced anything together. And that's just basic skills enabled to us to rotate around in design space and look at an object from 3 dimensions, just make sure things are packaged and fitting really nicely together. Now, another skill that our students will be able to engage with respect to CTE space is the actual definition of parts. In our Tinkercad space, we're able to focus on really basic shapes. This particular tool in the 3-dimensional design space is designed for learners starting as young as 3rd grade, all the way up as young at heart as you would like to be. And it combines lots of different categories and ways for us to think about objects in 3-dimensional space, whether that is in the architecture and interior design space, things like actual interior design seating sections. This is in collaboration between Tinkercad and the Oregon Museum of Science and Industry. You're able to pull in some design space elements and do design that way. When to delete that bubbly looking sofa and focus on some other things. In the case of the pandemic, we may have been removed for our younger students from our classroom household materials, and things like popsicle sticks or cardboard tubes or even pencils become something that we can access 3D. But what becomes really, really powerful for us is the ability to generate specific scientific shapes inside of Tinkercad. For example, I might be really focused on teaching my students about machining. And as we're learning about machining, we may be learning about fasteners. Sounds like a particularly boring subject, except for the fact that almost everything that you've ever used that's more than one piece has to be fastened together. If I'm taking one material and attaching it to another material to make a more complex object, I've got to figure out a way to have these things stick together. And glue is great, but glue and adhesives are not necessarily the best long-term solution from an environmental standpoint or from a user standpoint, especially depending on the materials. I, for one, would not like to use cookware that's been glued together as opposed to using fasteners. My students, me and my students and your students remotely, might pull out an ISO metric thread unit. In this case, this is an actual International Standards Organization metric thread for any fastener. Think a screw or a bolt. And what we can do is we can actually customize specifically what this fastener should look like. So what do we mean by that? Well, if we get a slightly better view of our thread, we can do things like adjust the actual diameter of this unit. I might be working with a really thick kind of bolt. This might be a nice, important engineering application. So let's say I might have a bolt that's 16 millimeters wide. You can see I'm actually just typing in those numbers into the inspector, and the thread is snapping where I want. I want this thread, I want this bolt to have really aggressive bite. So I'm going to change the pitch, the actual angle at which the thread is pointing as it spirals down the shaft of this bolt. It's not a really shallow 1.5 degrees, but instead I might go a little bit more aggressive. Let's go 3 times as aggressive and do 4.5 degrees on the pitch. And we'll see after a slight calculation by Tinkercad how thick now this thread has gotten. Really, really aggressive change that we see with this thread. We've got a simple number of rotations in the section. The entire thing is 25 millimeters tall. It's a really, really thick piece already. Almost looks more like an auger, something that you use to drill a hole. And there's 16 segments, but maybe I want to increase the number of rotations. So I'm going to slide and make this nice and big. And now what I can do is actually decrease the thread scale. So I'm making them nice and skinny. I want to make them a little bit taller now. So you can imagine that an accompanying bolt, something that's really thick, would be able to hold even a large bridge up. But the thing is, without focus on any particular technical specs, without a particular focus on the actual application, this is all theoretical right now because we haven't connected this to the kind of materials that we might use in the future. This is just the starting point, being able to build a specific shapes that we want inside of an online editor to allow our students to grow in their understanding of design skills. In this sense, we've only used some basic tools, just dragging and resizing shapes or changing the alignment of shapes or just being able to rotate the view and measure accurately. But as our students continue to grow, they'll gain other skills that will become integral to 21st century skills. And generative design, the idea that artificial intelligence is actually going to fill in some of the gaps, that we can teach the computer how to design an object that's doing what we want it to do. from a stress perspective, from a heat perspective, considering the materials, considering how the environment, the physical environment that the object will be used in will change over time. We can actually design parts and pieces that use less material and perform better than we might have been able to ourselves. More and more, we're going to lean into the space of actually printing circuit boards. Some of us may have heard of the shortage of computer chips that's making it hard to get a laptop computer or a cell phone right now. Designing the next generation of computer chips will be something that our students will be able to do in 3D first. And of course, simulation, to be able to simulate what a 3D printed object looks like and how it will perform in the real world becomes critical as well. So that's all fine and good to simulate printing, but what about simulate designing, but what about the actual physical printing of an object itself? What can we do to make that applicable for our students and help supercharge their learning, help them bounce back and get more gains even in the summertime? It's useful first to consider how a 3D printer works. And when you're working with a 3D printer, a form fusion filament printer, triple F style printer, which is what the vast majority of your students will work with and even finds lots of use in industry applications. You're just laying thin layers of material, one on top of another. And that material and the way that it's laid on top of each other, the temperature, the speed, this is very, very fast forward motion here. And the actual material itself really changes the quality and the ability for this material to get a job done. In your case, your students have more options available to them than you might have imagined and what they may have ever had before. For one thing, 3D printing at home is a legitimate option for many, many students. When we think about desktop printing, for our students who do have a little bit of extra space to carve out, what we're thinking about is a low-cost piece of equipment that will allow them to build all kinds of transferable skills. Many 3D printers, many serviceable 3D printers, many workable 3D printers, students have the ability to have access for those for the price of a new gaming console or less. This is something that once upon a time was multiple thousands of dollars for students to actually access, and now in the hobbyist space, our students are actually able to get in and get hands-on with the technology at a really low cost. When our students are working with this kind of technology, there are limits in the capacity and volume and the kind of materials they can use for a printer that's designed for desktop use. But really, many of us are familiar with what's happening in our actual schools and our career centers. Our technical spaces and our shops and our maker spaces that are designated for 3D printing. We get the amazing benefit of guided instructor support and hands-on real-time teamwork. Students who work with STEM are going to be working in teams continuously all the time. That's how we do our STEM work in the industry. But the thing about the school space, and students before and even now are realizing that 3D printers are not necessarily resource intensive, except for time. They're not the fastest machines in the world. And that means that while one student or one group of students is using the 3D printer, it may be difficult for other students to do the same. So while our printers may get bigger and may have bigger features and we may have multiple, now we're competing with other students and potentially other classes for time on this equipment. And that's something that might be remediated for our students, and we've seen it be remediated for some students in the actual use of production, actual printing as a service through printing farms. Once upon a time, if you didn't have a 3D printer, you weren't printing. Now you can take that file, that raw three-dimensional file that you generated, and send that off to a manufacturer whose sole job is to print it to your specifications. They don't design the thing. They could if you ask them to, but generally speaking, they don't design anything for you. You've done the design work and they're the hardware. That puts you in the space of being an engineering manager. You are, in fact, now tasking your production specialist, who you see an example of here, working at a 3D printer farm, just a building full of 3D printers, printing parts and pieces. You're managing that project. It is a little bit of a higher cost, however, and it's a lower hands-on work with the manufacturing aspect, but you're now focusing on critical engineering, management, and design skills that many students, engineering students included, don't really practice until they're in their master's level of engineering coursework. So 3D printing gives us really amazing flexible options. We're able to design remotely. We can print, we can slice remotely. We can take what we design and bring that to our schools, or invest in a 3D printer for home, or even farm that out to the 3D printing specialists who will then deliver that object directly for us. That's amazing. But what are some things that we can do in addition to understanding the capabilities of 3D printing to really help supercharge learning gain, to remediate that time that students didn't have and really make meaningful learning work? Well, the first thing that becomes critical to understand is that we want to make sure that we have work that's student-driven, that will work in our various learning scenarios. Less and less, we're seeing the not ready to return scenario go away. We are in the ready to return phase. School districts all over the country are seeing students return for summer education. We're preparing to go to a world where we're more careful. Many of us are vaccinated, and that means that we're transitioning from a learning at home space to a learning at school space, and that's going to be really, really good for the psyche of many of our students and educators. But in the event that we face another challenge that requires our students to go back remote, do we have something that can deal with that? And do we even have situations where we know we have special populations of students that will shift between a learning from home or learning at school environment? Different complex logistical considerations, but there are things that we can do that will work in both in-person and remote learning really, really well. The first is actually project-based learning. NextWaveSTEM, we love project-based learning. Something that we're doing and actively engaged in is the idea of infusing a project-based learning capstone into each one of our courses. And what we believe is that project-based learning builds a better foundation in science to expand into higher order technologies later on. So in order to build structures and manufacture products that meet both environmental and consumer goals, to really get into those constraints, and to make something that's usable, to design and build usable products, it takes time. And it takes time that many of our students lost out on thanks to the shifts that we have to make in the pandemic. So the idea now of getting away from our rote work and skills acquisition, but now focusing from the very outset on the particular problem we're trying to solve, the particular product we're trying to make, becomes critical. Once we build mastery of the 3D printing process, those skills in being able to program a 3D printer and doing 3D design, just operating the tools will transfer over into other computer-aided engineering and computer-aided manufacturing skills, whether that's working a CNC or whether that's programming specific data solutions that are going to be working in integrated technology. Once we understand the hard physical processes of design, these skills transfer over and make those accreditations and certificates much easier and to acquire, and we see that happen much more quickly. The second thing that becomes really good and really important for our students to do is actually to take the student-led work of PBL and really lean into it. Something that is difficult for us to do from the CTE space is to actually leave our students to themselves, it's become a little bit more easy for us to be helicopter instructors, because we do have the safety responsibility component of the machinery that we're working with as we're learning their technical skills. It's much more akin to apprenticeship than more traditional teaching. However, because student-led work is not just learning the skills, but really explaining out into the ways that we can solve the solution from a human-centered perspective, the student-led work now becomes things that can dominate our project-based learning experience. Yes, activities and workshops and lectures are great, but what might be more useful for us is actually simulating more and more learning optimization skills, modeling more and more in a 3D design phase, building and using the printer and iterating, being able to draft, being able to actually write our technical briefs. What we do from the very beginning is not necessarily even pigeonhole our students into a particular path, but it is not inconceivable that our students will be doing at least each one of these proposed student-driven activities throughout the entirety of a course. They should be doing everything at least once, and this list is nowhere near exhaustive. With the time that we've lost and the time that we get back, we now have this ability to dig into multiple modalities for expertise. Things that even go beyond what we consider as being integral to certification. Our students need remediation on how to be more intentional, devoted students. And the great thing about a diverse amount of student performance tests, different ways for us to benchmark our students and even provide those reflection points, is that we're also empowering our students in the different ways that they may be learners. We really dig into more and more what we mean by that in our project-based learning webinars. That's something that we're not going to cover today, but really looking forward to linking you all with that resource a little bit later on. So I know I hit you with a fire hose of information. You might be asking yourself, okay, Desmond, this is all great and good, but what can we do specifically? What are some actionable things that will take us to that next step as we seek to empower students in their CTE learning? Well, there are a few different things that NextWaveSTEM can do to help. And the first is in our coursework. Even if you are not a CTE teacher, but you know that in the future that we can't predict, students will need valuable hard and soft skills with respect to engineering and technology. Developing those skills through emerging technologies becomes critical. Our courses are K through 12 in robotics and AI, drones and coding, and 3D printing technologies. They scale up and they ramp up and they get your students familiar with using these technologies without a fear of failure of using these technologies. That removal of fear can be even a little bit scary for us as educators at times, but it's critical for our students to see themselves belonging in STEM. Our courses are designed to just build on a logical and taxonomically correct progression of knowledge through time. Our early learners are just getting their basic introduction. They're understanding what emerging technologies do and how they interact with the world from a very basic physical sense. Our 3 through 5 learners are building an understanding of real world applications. Not only what they do and how they work, but how they can be used to solve some problems. Our 6th grade students are actually evaluating the effectiveness of the solution. Can we be solving problems better? What are the pros and cons of the ways in which we're using these emerging technologies, and how can I develop skills to use them more precisely? And then in our 9 through 12 courses, our students are actually developing those real world solutions. They're considering real scenarios in the way that these materials, this emerging technology, can be applied towards them. We like to believe, and we've seen it in our customers here at NextWaveSTEM, that we're building students who are not afraid to learn about 3D printing, are not afraid to learn about robotics, or learn about flying drones, and students who have less fear and are ready to dive in, be hands-on right away, are students who are going to succeed and really excel in the career and technical education space. In NextWaveSTEM, we also like to say that we want to be your one-stop shop and give you everything that you need. Each one of our courses goes from 10 to 15 instructional hours in their lesson plans. We also are including equipment, making sure that you have 3D printers, drones, or robots, or whatever else you need to make sure that those courses can go off without a hitch. Our professional development and training is also done in a way in which that if you are a teacher who's never worked with a particular technology before, say you're not necessarily the STEM expert at your school, that's not a problem. Our courses are at this point designed to be introductory for students so that they can be captured at any level of their experience level. And we do that for our teachers as well. But we can also customize that professional development for what you need, going shorter or longer or more in depth with any of the course material, and also offering extra equipment. We want to make sure that you can get everything that you need to execute your courses. But on top of that, at NextWaveSTEM, if you are not the teacher, if you're looking for some extra help with the delivery of programming, it becomes a really, really useful thing if you can have a teacher come in and help you. NextWaveSTEM has a group of certified STEM professionals and instructors who can deliver courses in person and remote here in the Chicagoland area or remote in other markets. We want to make sure that we can be flexible to your needs and help get you through whatever situation you're in with respect to meeting your STEM goals. So we've got a couple more minutes left in the hour. As we were going, there's lots of information that gets really specific into career and technical education. I want to pause for a second. If you have some more questions about ways in which 3D printing can help supercharge and remediate that learning loss, help your students bounce back to those learning gains. The chat is open for any of those questions. I'm just going to pause briefly while those fingers are flying. And there's no such thing as a bad question with respect to 3D printing or career and technical education. Any questions that you might have, you can just throw them up in the chat. Well, I'm not seeing any questions so far, which is just fine. You may review this slide deck, or you may review this recording a little bit later on and say to yourself, I forgot to ask about that. That's not a problem. You can reach out to me directly. My email is really, really easy, Desmond@nextwavestem.com. I love digging into the weeds with questions. I love talking about 3D printing, emerging technologies in the coursework developed here at STEM. You about buying and getting this rolling with your own school. You can also find NextWaveSTEM on all major social media. You can find us on Twitter, Instagram, LinkedIn, and Facebook. We're not on TikTok yet, but that's something that may change in the near future now that we've got a couple of new interns. If you have those questions, reach out. We'd be happy to provide you with those answers. And you can take this right now as a personal invitation to our next webinar. Next week, we're going to be dealing specifically with project-based learning. We're going to be dealing with teaching drone coding using project-based learning. Some of our students have had experiences with drones. We want to answer those questions about challenges and problems that drones can solve even at home, considering that we're in the summer context and we're ready to make a swing back to the fall. That's going to be a really, really awesome webinar experience for us. Looking forward to seeing all of you there. And you'll be getting the links to register in the follow-up email from the webinar today. Everyone, I want to thank you so much for your time with us this afternoon. Wherever you are, we're hoping that you're staying safe and that you are well. We're also hoping that as you continue to prepare your students for careers using technology, that you are excited, that you are curious, and that you are really, really energized to build your students back up in this fall in ways that they've never been built before. Thanks so much, everyone. Have a wonderful rest of your day.